Hey everyone, Mr. Houck here. In today's video, we're going to be introducing the concept of matrices. Let's go ahead and get started. So what is a matrix? Well, a matrix is a two-dimensional rectangular array of numbers organized into rows and columns. Matrices are incredibly useful for organizing large amounts of data and are one of the most applied mathematical concepts outside of the classroom. Any application that collects large amounts of data likely makes use of matrices. Applications include economic modeling, maximizing profit, minimizing cost, scheduling, routing of shipments, and many more applications. Here's an example of what a matrix looks like. Again, notice that it's a rectangular array of numbers organized into rows. Rows run left to right, and columns, which run up and down. Okay? So the way that I always remember that is when you think about like the columns on a house or the columns in a building, the columns are the vertical structures that hold the building up. Okay? So think like architecture and the columns, that's how I've always remembered columns. And then rows again are the ones that are not columns, the ones that run horizontally, left and right. Okay? In mathematics, we typically name matrices with capital letters, such as this right here. This is matrix A, capital A. We describe the size of the matrix using its number of rows and columns and call this the dimension of the matrix. We might also see it referred to as the order of the matrix. When describing the dimension of a matrix, we always list the rows first, left to right, and the columns second, up and down. In the example above, matrix A is a 3x4 matrix. That's how we say this right here. When you see this 3 with a multiplication symbol in the middle, that means 3x4. So matrix A is a 3x4 matrix since there are 3 rows, 1, 2, 3 rows, and 4 columns, 1, 2, 3, 4 columns. The numbers that appear in the rows and columns in the matrix are called the elements or the entries of the matrix. While the matrix itself is named using a capital letter, such as right here, the elements of a matrix are named using lowercase letters with subscripts that describe its location in the matrix. The first number in the subscript represents the row, while the second number represents the column. In the example to the right, element A23 represents the number in matrix A that is in row 2 and column 3. And really I should have said A subscript 23. So for example here, A subscript 23 is right here. I'm going to go ahead and highlight that. And notice that A subscript 23 is in the second row. 1, 2, 3, second row, and the third column. So the intersection of the second row and the third column is element A subscript 23. In some textbooks, you'll see the row and the column separated with a comma. So you might see something like, instead of A subscript 2, 3, you might see A subscript 2, comma 3 to further emphasize that 2 is the row and 3 is the column. So let's talk about some special matrices that we're going to define now, but come back to more later in this unit. So a matrix that has the same number of rows and columns is called a square matrix. In this example, notice that we have 1, 2, 3 rows and 1, 2, 3 columns. This would be a 3x3 matrix. And since the rows and columns, they have the same number of rows as they do columns, matrix A here would be a square matrix. A matrix in which every single element is 0 is called a zero matrix. Notice here in matrix B, every single element or every single entry in the matrix is the number 0. A square matrix that has 1s for every entry on the main diagonal and 0s for all other entries is called an identity matrix. So notice here in matrix C, on the main diagonal here, all the entries are a 1, and everywhere else, the entries are all 0s. Again, we call this an identity matrix. A matrix that has only one row is called a row matrix. One row can have any number of columns here. So this would be in this example, this would be a 1x4 row matrix. And a matrix that has only one column and any number of rows is called a column matrix. Notice in this example we have 4 rows, but only one column. Okay, again, these are all just definitions that we need to establish. All right, so let's get into some problems here. In the first example problem, we want to define the dimensions of the matrix. Remember that we define the dimensions of the matrix as the number of rows by the number of columns. Well, we have 2 rows by 1, 2, 3 columns. So this would be a 2 by 3 matrix. And again, I'll just go ahead and put this is row 1, row 2, column 1, column 2, column 3. In our second example, for the matrix provided, what is F sub 2, 3? Well, remember that using the lowercase letter, we're talking about a matrix element, and 2 is representing the row, and 3 is representing the column. Let's go ahead and write that out here. So we're looking at F sub 2, 3. Again, 2 is representing the row number, 3 is representing the column number. Well, let's see here. Row 2 is right here. Column 3 is right here. So row 2, column 3 would give us the entry 2/7. In our next example, is it possible to have a 2 by 3 identity matrix? Why or why not? Well, let's look back at the definition of identity matrix. So to be an identity matrix, a square matrix that has 1s for every entry on the main diagonal and 0s for all other entries is an identity matrix. Notice it says a square matrix, and we define square matrix as a matrix that has the same number of rows and columns. Well, if you have a 2 by 3 matrix, the number of rows, 2, is different from the number of columns, so this cannot be a square matrix. And if it's not a square matrix, it can't possibly be an identity matrix. So we would say no. All identity matrices must be square matrices. Okay, all identity matrices must be square matrices. Again, meaning that they have to have the same number of rows as they do columns. All right, our next example, would the matrix below be considered an identity matrix? Why or why not? Well, this time, this is definitely a square matrix. We have 1, 2, 3 rows, 1, 2, 3 columns. But is this an identity matrix? Well, if we go back again to the definition of identity matrix, we have to have 1s for every entry on the main diagonal and 0s for all other entries. Well, if we look at the main diagonal, we don't have 1s for every entry on the main diagonal. So this would be no. Again, no, because identity matrices have 1s on the main diagonal. Okay, so an example of an identity matrix that's a 3 by 3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1. That would be an identity matrix because we can see that we have 1s on the main diagonal and every other element or every other entry in the matrix is a 0. For our last example in this section, we want to write the matrix with elements C sub 1, 1 equals -9, C sub 1, 2 equals 3, C sub 2, 1 equals 4, and C sub 2, 2 equals -4. Well, let's go ahead and first notice that these are lowercase c's, meaning that the name of the matrix is capital C. And it's looking like we have 2 rows and 2 columns. So the first row, first column should have a -9. First row, first column. The first row, second column should have a 3. It's right there, first row, second column. The second row, first column should have a 4. And the second row, second column should have a -pi. Okay, so pretty easy to set up if you know your matrix elements. So now that we've talked about the basics and the terminology involved with matrices, let's look at a couple of operations, starting with addition and subtraction today. So if 2 matrices have the same dimension, I'm going to highlight this. If 2 matrices have the same dimension, they can be added or subtracted. Let's see an example of matrix addition and subtraction, starting with addition here. So matrix A is going to be a 2 by 3 matrix. Matrix B is also a 2 by 3 matrix. So they both have the same dimension, meaning they can be added and subtracted. So here's how addition would work, and it's pretty straightforward here. If I want to add matrix A plus matrix B, so A plus B, then I'm simply going to add the corresponding elements. So for matrix A, row 1, column 1 is 6. For matrix B, row 1, column 1 is -6. So we'll have 6 plus -6. For matrix A, row 1, column 2 is -3. For matrix B, row 1, column 2 is 7. So in the sum, we will have -3 plus 7. And we're going to continue on in this fashion. We'll have 0 plus -1 for row 1, column 3. We'll have 14 plus -7 for row 2, column 1. For row 2, column 2, we'll have 1/2 plus -5 halves. And for row 2, column 3, we'll have -pi plus 3pi. Now, simplifying, 6 plus -6 will give us a 0. -3 plus 7 would give us 4. 0 plus -1 will have -1. 14 plus -7 would be +7. 1/2 plus -5 halves would be -4 halves, which would reduce to just -2. And then -1pi plus 3pi would be +2pi. So this would represent our sum of matrices A and B. Notice that the sum of the matrices is also going to have the same dimensions as the individual matrices. A and B were both 2 by 3 matrices, 2 rows, 3 columns. The sum A plus B also has 2 rows, 3 columns. Now let's do a problem with matrix subtraction. So in this example, using the same matrices A and B, we want to calculate B minus A. All right, well, B minus A, we want to make sure that we're going in the correct order. So starting with B, we're starting with the elements of B, subtracting the elements of A. So in row 1, column 1, that'd be -6 for B, minus the row 1, element 1 entry for A would be +6, so -6 minus 6. Row 1, column 2, we're going to have 7 for B minus -3 for A. And I'll start highlighting these. Then we'll have -6 minus 6. Oh, I already did -6 minus 6. That was that first one there. Got mixed up. We'll do -1 minus 0. There we go. Small mistake on my part. Then we're going to have -7 minus 14. We're going to have -5 halves minus 1/2. And then lastly, we'll have 3pi minus -pi. All right, simplifying, Negative 6 minus 6 will get us negative 12. 7 minus negative 3 will get us positive 10. Negative 1 minus 0 will get us negative 1. Negative 7 minus 14 will get us a negative 21. Negative 5 halves minus 1 half would be negative 6 halves. Negative 6 over 2 is a negative 3. And then 3 pi minus negative pi would get us a 4 pi. Okay, so matrix addition, matrix subtraction, pretty simple process. Now, I want to show you how we can check our work. And it turns out that Desmos has a matrix calculator that we're going to be taking advantage of. So let's go over to Desmos so we can see how to do this in the matrix calculator. All right, so here we are with Desmos. And I'm just going to go ahead and full screen it here. So this is desmos.com/matrix. I'm going to put this on eClass for us. But let's go ahead and double check these matrices. Now, in Desmos, anytime we want to create a new matrix, we can click the New Matrix button. If it's the first matrix, it's automatically going to name the matrix A. There's no worries there. If we look at our notes, matrix A and matrix B were both 2 by 3 matrices, so 2 rows, 3 columns. I'm going to click the plus button for columns to turn it into a 2-row, 3-column matrix. Let's go ahead and put in our matrix elements. So matrix A had a 6. Now press the right arrow, a negative 3. Press the right arrow, a 0. Pressing the right arrow again will take us down to the second row here. Then we had a 14, a 1/2, so I'm going to do 1 divided by 2. Press the right arrow a couple times, and a negative pi. Now here's the thing. In this Desmos matrix calculator, it cannot handle pi as a variable. So let's go ahead and instead of saying negative pi, let's just use negative 3.14. We understand that's going to mean negative pi. Now, clicking the enter button is going to take us to a new line in the matrix calculator. I also want to put in matrix B, so I'm going to click matrix. I'm going to click new matrix again. Once again, matrix B was a 2 by 3 matrix, so I'm going to click the plus button for the columns to make it a 2 by 3. And let's put in the elements of matrix B. So matrix B had a negative 6, a positive 7, a negative 1, a negative 7, a negative 5 halves, so I'll just do negative 5 divided by 2, and a 3 pi. Now again, for some reason the Desmos matrix calculator can't handle pi as the variable pi, so instead of saying 3 pi, we'll do 3 times 3.14. Okay, hit the enter button, and let's see what happens when we try to do a plus b and b minus a like our examples on our notes. So first we'll do a, so again we call the first matrix a, so a plus b. And we can turn these into decimals, we can turn them into fractions with that little button over there that looks like a fraction. So if we go back to our notes, a plus b, for the answer we got for row 1, 0, 4, negative 1, so that's matching. And then we got 7, negative 2, 2 pi. And remember that 2 pi is 2 times 3.14, which would be 6.28. So this turns out to be correct. Now let's double check b minus a. So b minus a. And on our notes, we got for row 1, negative 12, 10, negative 1, which we have here, negative 21, negative 3, and 4 pi. 4 pi estimated to a decimal would be 12.56. So we can see that we can use this Desmos matrix calculator to double check our work, and as the unit progresses, this Desmos matrix calculator will actually do a lot of the tedious work for us. All right, so going back over to our notes here, we have a few extra practice problems down at the bottom. I would encourage you to pause this video, try those problems, unpause the video, and check your work. But let's go ahead and look at the solutions to the 3 practice problems at the bottom. All right, for the 3 practice problems at the bottom, for a plus b, this is what I'm getting. getting 14, 17 for row 1, negative 8, 3 for row 2, 4, 2 for row 3. I checked these with the Desmos matrix calculator, so these should be correct. For the second practice problem, matrix C minus matrix D, I'm getting 2 pi minus 6 for row 1, 1 minus square root of 3 for row 2, and positive 1 for row 3. If you estimated 2 pi minus 6 and 1 minus square root of 3 as decimals, that's perfectly fine. If you double check in the matrix calculator on Desmos, they will be estimated as decimals. Okay. For the last example problem, for A plus C, well, if you tried it in the matrix calculator on Desmos, you're going to find a little error message. And the reason is because we cannot add these matrices because they have different dimensions. Remember that in order to add or subtract matrices, they must have the same dimension. So I'm going to write right here, we cannot add or subtract matrices with different dimensions. All right. Can I add or subtract matrices with different dimensions? So this has been our introduction to matrices. We saw some basic terminology. We understand what a matrix is, how to write a matrix. We understand, the dimensions of the matrix, the entries of the matrix. We saw some definitions like zero matrix, identity matrix, things like that. And we also saw addition and subtraction of matrices. In the next video, we're going to be looking at scalar multiplication with matrices and also multiplying matrices by other matrices. Look forward to seeing you in the next one.